Hi, good morning, students. How are you all? I hope all you are safe by God's grace. And also, I hope that you might have completed the homework of the last class, isn't it? Okay, shall we move to the today's class? See, in this maths class, we are going to learn properties of inverses in matrices. Okay, properties of inverses of matrices that we are going to learn like theorems. See, theorem 1.4 says that if A is a non-singular, then determinant A inverse is equal to 1 by determinant A transpose the whole inverse is equal to A inverse the whole transpose, lambda A the whole inverse is equal to 1 by lambda into A inverse, where lambda is a non-zero scalar. Moreover, we know that x inverse means how we will be writing 1 by x, ordinary number matrix. We cannot write like that. Okay, shall we move to the proof? See, proof. Let A is a non-singular, because they have mentioned if A is non-singular, so we too have to take the matrix as a non-singular matrix. We know that if A is a non-singular matrix, the determinant A will be not equal to 0. If determinant A not equal to 0, then A inverse exists. And we know that A into A inverse is equal to A inverse into A is equal to In. We have taken it as equation number 1. See, for the first one, since it is determinant, we will take determinant on equation 1. Since second one is with the transpose, we will take transpose on this equation 1. Okay. See, for the first one, we have taken the determinant on all that. Determinant A into A inverse equal to determinant A inverse into A is equal to determinant In. Two matrices are there inside the determinant. See, by the product rule of determinant, that is determinant A into B can be written as determinant A into determinant B. So, such a way this also we can able to write it as determinant A into determinant A inverse is equal to determinant A inverse into determinant A equal to 1. See, determinant In I have written it as 1. How? See this I2, that is identity matrix of order 2. See 1 0 0 1. How we will do? Multiply 1 minus 0, we will be getting it as 1. Same way, see 3 by 3 matrix 1 0 0 0 1 0 0 0 1. We know that since all the elements are 0 in these two and here, it is enough to multiply only the diagonal. So 1 into 1 into 1 is 1. So it's very clear that determinant of an identity matrix will be equal to 1. Now only 1 I have taken it, okay. Determinant A into determinant A inverse is equal to 1. So from this, what is determinant A inverse? Determinant A inverse is equal to 1 by determinant A. Is it clear? This is what the first proof. Very simple. See, for the second proof, as I said that it's related to transpose, that equation 1 we can take transpose on all that. A into A inverse the whole transpose equal to A inverse into A the whole transpose is equal to In the whole transpose. See, we have learned from grade 10, that is AB the whole transpose is equal to, what is that, B transpose into A transpose. The same thing we are using here. So we may get A inverse the whole transpose into A transpose equal to A transpose into A inverse the whole transpose equal to In. Actually, what is this? See, shall we equate it along with this? A into A inverse equal to A inverse into A is equal to In. Or we have learnt that AB is equal to BA is equal to I, implies A is the inverse of B or B is the inverse of A. So here we can write either A transpose inverse is A inverse the whole transpose, or A inverse the whole transpose inverses A transpose, right? So such a way when we take, we can write A transpose the whole inverse is equal to A inverse the whole transpose. This is what the second proof. A transpose the whole inverse can be written as A inverse the whole transpose. Okay. For the third one, again I have taken that equation 1. A into A inverse equal to A inverse into A is equal to I. Equation number 1. The same equation I have written again. And there we have lambda. So I'm taking, since lambda is a non-zero scalar, I'm just going to multiply here. See here, lambda A into 1 by lambda into A inverse is equal to 1 by lambda into A inverse into lambda A is equal to In. See, if I cancel this lambda into lambda and 1 by lambda, we will be getting A inverse. So without the changing the value, I have written the lambdas. Now the same thing, A into B equal to B into A is equal to I. So it's very simple. A is the inverse of B. So I can write lambda A, the whole inverse is equal to 1 by lambda into A inverse. Is it clear? This is what the first theorem. What is that? The theorem says that if A is a non-singular, then determinant A inverse equal to 1 by determinant A transpose the whole inverse equal to A inverse the whole transverse, lambda A the whole inverse is equal to 1 by lambda into A inverse, where lambda is a non-zero scalar. Okay, shall we move to the next one? Now, theorem 1.5, that is left cancellation law. See, let A, B and C be square matrices of order n, and if A is a non-singular and AB equal to AC, then B is equal to C. So ABC are square matrices of order n, A is a non-singular and AB equal to AC means what we should get it? B is equal to C. Okay, this non-singular condition, let me take it. Let A is a non-singular. So we know that non-singular means determinant A is not equal to 0. Therefore, we know that A inverse exists. Now, the given condition is AB equal to AC means we should get the answer B equal to C. I have taken the condition given AB equal to AC. Now, pre-multiply by A inverse. Pre-multiply this by A inverse. See, both A is in left hand side, so we are multiplying in left. Pre. Post means we have to multiply in the right side. Okay. See, A inverse into AB equal to A inverse into AC. Just change the bracket because matrices accept this associative property. Since matrices hold this associative property, you can change the bracket. A inverse into A into B equal to A inverse into A into C. See, A inverse into A, that is identity In. Here also A inverse into A, In. In into B is equal to In into C. See, identity matrix into any matrices, we will be getting the same matrix, right? We know that A into I is equal to I into A is equal to A. So here we will be getting B is equal to C. Very simple, isn't it? This is left cancellation law. Right cancellation law is left for your work. Okay. See, let me give that theorem. Theorem 1.6 is right cancellation law. The same thing. Let A, B, C be square matrices of order n. If A is non-singular and BA equal to CA, then B equal to C. So it's very simple to prove, isn't it? So first you can take the condition non-singular, then A inverse exists, post multiply by A inverse. So A inverse will come in this right side. Automatically you will be getting B equal to C, isn't it? So do it as your work. Okay. So right cancellation we have learned and left cancellation. Now, if it is non-singular, we will be getting BA equal to CA means B equal to C, isn't it? But at the same time, if A is singular, see the note, if A is singular and AB equal to AZ or BA equal to CA, then B and C need not be equal. It's not necessary to be equal, okay? If it is non-singular, it will be equal, but if it is singular, may be equal or may not be. So it's not must to be equal, okay? Shall we move to the next one? Now, theorem 1.7, reversal law of inverses. Reversal law of inverses. If A and B are non-singular matrices of the same order, then the product AB is also non-singular. and AB the whole inverse is equal to B inverse into A inverse. See, if A and B are non-singular matrices of same order, if we take two non-singular matrices, then we should prove that the product is also non-singular, and moreover AB the whole inverse is equal to B inverse into A inverse. What is the meaning of this? Inverse of AB is B inverse into A inverse. In otherwise, if we read, inverse of AB is B inverse into A inverse. Shall we prove? This is also very simple. See, I have taken let A and B are non-singular. Non-singular means what is the meaning? Determinant A also not equal to 0. Determinant B also not equal to 0. Therefore, what happens? A inverse and B inverse exist. Also, what we know it? Determinant A into B using that product rule. Determinant A into determinant B. Determinant A also not equal to 0. Determinant B also not equal to 0, right? So, then automatically this is not equal to 0. Therefore, what happens? AB inverse exists. So, one thing we have proved. Now, the next thing, AB the whole inverse equal to B inverse into A inverse, we need to prove. Yeah, this is what AB the whole inverse equal to B inverse into A inverse, we have to prove. For that, let me find it out. What is AB into B inverse into A inverse? See, very simple. Since matrices hold that associative property, I can change the bracket. See, B into B inverse is equal to A inverse. We know that B into B inverse means what is that identity element? In. Now, when we multiply any matrices with identity element, we will be getting the same matrices. So, A into A inverse. Now, again A into A inverse, same matrix, isn't it? Inverse and the same matrix, we will be getting identity matrix In. Let it be. Now, multiply like this, B inverse into A inverse into AB. Same procedure, change the bracket. B inverse into A into B. A inverse into A is In. Now, again we know that when we multiply with the identity element, we will be getting the same matrices, that is B inverse into B. Again, we have to use the inverse property, that is In. So, what we have got it? AB into B inverse into A inverse equal to B inverse A inverse into AB is equal to In. That is AB equal to BA equal to In. So, what we can say? A is the inverse of B or B is the inverse of A. Here it is very simple. AB the whole inverse is equal to B inverse into A inverse. After inverse of AB is B inverse into A inverse. Is that clear? Shall we move to the next one? That's theorem 1.8. Law of double inverses. Double. If A is non-singular, then A inverse also non-singular, and A inverse the whole inverse is equal to A. So, what are the things we need to prove? If A is a non-singular, then A inverse is also non-singular, and A inverse the whole inverse is equal to A. See, assume A is non-singular. Non-singular means what are the things will be there? Determinant A not equal to 0, then automatically A inverse exists. Say, the first theorem today what we learnt is determinant A inverse is equal to 1 by determinant A. Automatically this is not equal to 0 because determinant A not equal to 0 means 1 by determinant A. This is not equal to 0 means 1 by that value is also not equal to 0. So, what happens? A inverse is also non-singular. Determinant A is non-singular means determinant A not equal to 0. The same way, if determinant A not equal to 0 means we will be able to say is A is non-singular. The same thing, if determinant A inverse is not equal to 0, what we can say? A inverse is also non-singular. Okay, so one proof we have did. Now we are supposed to prove A inverse the whole inverse is equal to A, or inverse of A inverse is A. Is it not? Okay. For that I am taking the condition we know already A into A inverse is equal to A inverse into A is equal to I. Now I have taken only one. A into A inverse is equal to I. Find out the inverse of both. A into A inverse the whole inverse is equal to I. Identity inverse is also equal to I the same way. The same step I have written again. A into A inverse, the whole inverse is equal to I. See, just before we learned reversal, isn't it? AB, the whole inverse is equal to B inverse into A inverse. Such a way when we write, what happen? A inverse, the whole inverse is equal to into A inverse is equal to I. A inverse, the whole inverse into A inverse is equal to I, using this. Okay, now post multiply by A. That means right side we have to multiply. A inverse, the whole inverse into A inverse into A is equal to I into A. I into A means we know that is A. Here, just to change the bracket, A inverse, the whole inverse into A inverse A. We know that A inverse A is I. Now, A inverse, the whole inverse into I is equal to A. So, here into I, when we multiply any matrix is the identity element, we will be getting the same matrix, that is A inverse, the whole inverse is equal to A. Is that clear? So today we learned 5 theorems. Is it not? Very simple one. The first one with 3 subdivision, the second one is left cancellation law, then right cancellation law, then fourth one is reversal law, isn't it? Reversal. AB the whole inverse equal to B inverse into A inverse. This is using double inverse. A inverse, the whole inverse is equal to A. Now the last theorem. Now the last theorem is theorem 1.9. That is, if A is a non-singular matrix of order n, then this all using that adjoint. Okay. Adj A the whole inverse is equal to adj A inverse is equal to 1 by determinant A into A. The second one is mod determinant at GA is equal to determinant A power n minus 1. We will be using this in the problems also, okay? Determinant at GA will be equal to determinant A power n minus 1. The third one, adj of at GA is equal to determinant A power n minus 2 into A. Determinant A power n minus 2 into A. This also we need to use. And fourth one is adj of lambda A is equal to lambda power n minus 1 into adj A. Suppose if it is adjoint of 3A, then 3 power, if the order is 3 power 3 minus 1 into adj A. Or if let be the lambda value will be equal to 5. Adj 5A is equal to 5 power n minus 1 into adj A. N is the order of the matrix. If it is 3 by 3 matrix, 5 power 3 minus 1. That is 5 square, 25 into adj A. Now, determinant of adj A is equal to determinant A power n minus 1 the whole square. Determinant A power n minus 1 the whole square. And the last one is adj A the whole transverse equal to adj of A transverse. See, adj A the whole inverse also equal to adj A inverse. Adj A the whole transverse equal to adj A transverse. Okay, this all we have to use in some of the problems. So don't forget to learn this. Okay. In the next class we will be using this to do the sums. See, note, if A is a non-singular matrix of order 3, we have taken order 3, then what happens? We know that since it is non-singular, determinant A is not equal to 0. Just now we learned that adj A will be equal to determinant A power n minus 1. N is order of the matrix. So as per that, when we find out determinant adj A is equal to determinant A power 3 minus 1, that is determinant A the whole square. See, from this, what is determinant A? This is square, isn't it? Plus or minus root determinant adj A. Plus or minus root determinant square root of determinant adj A. This is, see, don't get confusion. X square is equal to 4 means what we will write? X is equal to plus or minus root 4, right? The same thing. Determinant A the whole square is equal to determinant adj A. So determinant A is equal to plus or minus root determinant adj A. See, we have that inverse formula. A inverse is equal to 1 by determinant A into adj A. See, A inverse, determinant A, what we have got it, plus or minus root, determinant at GA. So we may get it 1 by plus or minus root, determinant at GA into at GA. We can think that, isn't it, why we are doing this? See, actually in some problems, at GA will be given. At GA will be given and they will ask us to find out what is A inverse. In the last class, you might have did the homework also when A is given, how to find out A inverse. Suppose if at GA is given, how will you find it out A inverse? For that only, we have to learn this formula, okay? When at GA is given and A inverse is asked, we will be using this, that is A inverse is equal to 1 by plus or minus root of determinant at GA into at GA. Okay, see, also in that fourth part I think, so this is adj of at GA is equal to determinant A power n minus 2 into A. Adj of at GA is equal to determinant A power n minus 2 into A. From that, here we have taken the order 3. Since it is order 3, adj of at GA will be equal to determinant A power 3 minus 2 into A. 3 minus 2 is 1. So adj of at GA will be equal to determinant A into A. From this, what is A? That is 1 by determinant A into adj of at GA. 1 by determinant A into adj of at GA. So, A is equal to 1 by determinant A. Actually, determinant A using at GA, what is that? Plus or minus square root of determinant at GA. So, if we use the same thing in this determinant A, we will be getting 1 by plus or minus root of determinant at GA into adj of at GA. So, these two formulas is must. Okay, this one and this one. This is when if at GA is given and A inverse is asked, we will be using this formula. And if at GA is given, if A is asked, at GA given and A is asked means what is the formula? 1 by plus or minus square root of determinant at GA into adj of at GA. Adj of at GA means what is that? For the adjoint, again we have to find out the adjoint. Let me recall it. How will you find it out? At GA, what is the formula of at GA? Are you remembering? Aij, the whole transverse. What is Aij? Cofactor. Transverse of the cofactor matrix gives at GA. Now, adj of at GA means what is the meaning? For the at GA, we have to find it out. See, adj of at GA is equal to at Aij, the whole transverse. Okay, for that we will be finding the Aij and we will find out the transverse. Is that clear? So these two formulas is very important. Using this, we have to do the sums, that we will do it in the next maths class. Okay. Today we will do one problem. Okay. See example 1.4. If A is a non-singular matrix of odd order, prove that determinant at GA is positive. If A is a non-singular matrix of odd order, prove that determinant at GA is positive. Okay, see here, since they have given odd order, we can take it. Let A be a non-singular matrix of order 2m plus 1. Normally we will use n, since n is of order of the matrix here, we have taken m. Okay, 2m plus 1, m can be 0, 1, 2. When we substitute 0, what happens? 1. When we substitute 1, that we may get 3. When we substitute 2, 2 into 2, 4 plus 1, 5. So, all will be with the odd numbers. Now, we know that determinant at GA is equal to determinant A power n minus 1, isn't it? In the last theorem, that is theorem 1.9, the first property is that one. Now, when we substitute n, what is the order n? 2m plus 1. So, determinant A is power 2m plus 1 minus 1. 2m plus 1 minus 1. Plus 1 and minus 1 will get cancelled and we will be getting determinant A power 2m. What does this says? Power is even, right? Even when the determinant A is negative, since the power is even, automatically we will be getting a positive. That's what implies is always positive. Therefore, what is that actually? Determinant at J. Determinant at J is positive. It's also like a theorem, isn't it? Okay, that's why I have taken today. Tomorrow's class onwards, we will be doing the problems using all these theorems, especially using RGA. RGA will be given and they will ask, find what is the matrix A. And RGA will be given and they will ask, what is the matrix A inverse. Okay, this all we will be doing in the next class. I hope all you might have understood. Today there is no homework. Only in one theorem I have given you to do as learn all these theorems and the result. Okay. Thank you students. Bye-bye.